Welcome to Quantum Leap. Now we are going to discuss constraints. What are the constraints? If the motion of a particles or system of particles is restricted by one or more conditions, then we can call the constraints, or we can say the limitations on the motion of systems are called constraints, and the motion is said to be constraint motion. Constraints are classified into three types. They are holonomic constraints, non-holonomic constraints, and forces of constraints. First, we need to discuss holonomic constraints. Constraints limits the motion of system and the number of independent coordinates needed to describe the motion is reduced. For example, if a particle is allowed to move on the circumference of circle, then only one coordinate theta is sufficient to describe the motion because the radius of the circle remains same if r is the position vector of a particle at any angular coordinate theta related to the center of the circle, then we can write this equation modulus of r equal to a r minus a equal to 0. This expression is known as the constraint for particle in circular motion, since the circular motion of particle to need a one independent coordinate, that is theta. Therefore the number of degree of freedom is system require is 1. So this is our circumference of the circle. So here the r is the constant. This is r. A, sorry, radius of the sphere is, it is denoted by a. This r is the position vector of the system. This is one of the example of a holonomic constraint. Next example, in case of simple pendulum with a rigid support, the constraints during the motion, the distance L of the bob particle from the point of suspension remains constant with the time. Thus, if r is the position vector of the particle related to the position of the suspension, then the condition of constraints can be expressed as modulus of r equal to L constant. So this is our simple pendulum. This is length of the pendulum, and this one is if it is get, if you give some force, it will get oscillate. Then this is the uh, degree of freedom of the simple pendulum. Here the motion is confined to the move in a vertical plane. Only one coordinate theta and angular displacement is sufficient to describe the motion. Therefore the degree of freedom is 1 here. This only theta is enough. So if the constraints are present in the system of n particles, if the constraints are expressed in the form of equation, so this equation, then this is known as a holonomic constraint. Next, non-holonomic constraint. The constraints which are not expressible in the form of equation are called non-holonomic constraints. For example, this is the equation which expresses by the constraints not equal to 0, whereas in previous case equal to 0. So if you look at the some examples here, the first example which we are going to see here, this is a sphere and radius of the sphere is a. Position vector of the particle related to the center of the sphere is r. The mass of the system is m. So the motion of a particle placed on the surface of the sphere, radius a, will be described by the this equation, where the r is the position vector of the particle related to the center of the sphere. So if you clearly look at it, the position of the system somewhere it is there. So it may lose the contact of the body in halonomic cases. Okay, remember this word. In non-halonomic cases, the body might be lose the contact. Halonomic cases, maybe it will not happen. And one more example: the gas molecules in a container are constrained in moving inside the gas container. If the gas contained in the shape of sphere with the radius a and r is the position vector of a molecule, then the condition of constraint for the motion of molecules can be expressed as this equation: modulus of r is equal less than a. So because here the radius is going to decrease, right, when we are compress the gas molecules, when we apply the pressure, um, I mean gas molecule is going to be the compress. Second example, rolling disk. Let us consider the disk rolling on a rough horizontal plane with a condition of constraints. The plane of disk is always vertical. So this is another example of non-halonomic constraint. Further constraints are classified into two types. One is Rheonomous, another one is Scleronomous. What is Rheonomous constraint? So this equation f of r expressed in the form of the equation of constraints consists of the time as explicit variable. Then the system we can call that a Rheonomous constraint. So if it is not time dependent, then we can call that Scleronomous constraint. So this is what we are express the equation in the form of constants. In this case, they are not explicitly depends on time. So further, these constants, Scleronomous constants, are divided into two types. One is conservative, another one is dissipative. So conservative, we all know in these systems, the total mechanical energy of system is conserved during the constraint motion, and the constraint force do not do any work. This one is do, not d. Okay, so please correct this one. So dissipative constraints in the systems, the constraint forces do work and the total mechanical energy not conserved. So these are the real case systems, dissipative systems. Okay. Next, final constraint, forces of constraints. The constraints are always related to the forces which restrict the motion of the systems. These forces are called forces of constraints. For example, the reaction force on a sliding particle on surface of the sphere is the force of constraint. Next one, in the case of rigid body, the inertial forces of acting on a reaction between any two particles are the force of constraint. Third example, a body slide on a frictional surface, the work is done by the force of constraint. So for the real displacement, these are the frictional force. So these are all about constraints. So we need to discuss another topic, maybe that is generalized coordinates. Next topic, generalized coordinate. Next one is principle of virtual work. Then D'Albert's principle. Thank you.